welcome back, everyone, to this session. I'm not only a Java guy, but also a database guy, so I'm really looking forward to this talk with Zoe on how to choose your right database for your application. Welcome.
Awesome. All right, let's go ahead and get started. So I'm going to be presenting how to choose the right database for your application. So if that's not the talk you're here for, please feel free to exit now. Let's go ahead and get started. So my name is Zoe Steinkamp. I'm a developer advocate for a company called Influx Data, or InfluxDB. We are specifically a time series database. You can find my LinkedIn here. As you can tell by the way that I talk, I am from the United States. I'm from specifically Colorado, which is similar to Sweden in that we're mountainous and snowy as well. I've really been enjoying it here. It's beautiful weather this week. So this is going to be the overview of what we're going to be talking about. So first thing, we're going to go over the database ecosystem as of 2023, 2024, what actually makes different types of databases perform differently from a technical perspective, and when to use a specialized versus a general purpose database. So really quick, some history. This is about the SQL language, not the database, although they do tend to share similarities. And it's very confusing when you talk to people non-technical and you go, SQL DB, you write SQL to query it. And they're like, what does that mean? And you're like, well, SQL DB normally indicates to us as it's a relational database that almost all relational databases query with the SQL language. But many NoSQL DBs also query with the SQL language. Many also have their own. But basically, SQL was originally developed in the 1970s. These were the first 10 commands that you would have had in the 1980s. And from what I understand, they weren't actually added to for about, I want to say, 5 to 10 years. So for a while, this was all that you had. Though in all fairness, they were really good because they're still with us and probably the most commonly 10 used that are today. So that's when it first came into our lives. So this is the evolution of databases. So you're going to see our SQL DBs over there started, like I said before, technically the 1960s, but really 1970s, 1980s is when things actually took off and you could really start to use them. Fun little fact, tidbit about the SQL language. When they originally built those first 10 and when they originally built the SQL language, at the time, you had to be very technical to use computers back then, just like nowadays. But in their minds, they actually created the SQL language with the idea that non-technical people would be able to interact with the database and get information out of it. They, later on in the 1995-ish time, they interviewed them and asked about it, and they were like, we're kind of sad that nowadays there's a database engineer. They're like, we really thought that this would be used by a broader audience as the World Wide Web now is used in the 90s. And they were like, that's kind of sad. But you know what? It turned out pretty good for them, all things considered. It did become one of the largest non-coding languages out there. So in the early 2000s, we also start to get our first NoSQL non-relational DBs. We get Mongo and Cassandra. Then in the early 2010s, we get our graph DBs, Neo4j and GraphDB, for example. Neo4j is actually here sponsoring at their booth. And those are what power the social media revolution that we've all come to enjoy. In the mid, like 2015-ish range, roughly, we start to get time series databases, like my company. Those come about mainly because we start working more with IoT devices, industrial IoT. Things just start to get a lot smarter. That's also when we start actually monitoring really like our web infrastructure. Things like Datadog, for example, that would be using most likely some type of time series database on the underside to keep some of your metrics and such. That's all being powered by time series databases to actually start doing real-time monitoring, basically. And now, they've actually been around a lot longer than the 2020s, but vector DBs have definitely been having their moment, you could say. They've actually been around for a while. They've always been used for things like image search, for example. If you've ever taken a photo and Google image searched it, that was being powered by vector DBs. Just a more basic version than the one we've all come to know, like ChatGPT. And this is basically how these two are imagined. So you've got your SQL. Again, technically, Relational Database Management System is their full name. Everyone just calls it SQL DB, though, because that's a lot of words. And then our NoSQLs. And those are stored slightly differently. You've got your key value pairs. That's going to be things like Redis. You've got your document store. That's going to be Mongo and MongoDB. You've got your columnar store, which includes time series databases like the one I work for. And then you have your graph. And that's going to include graph DBs and vector DBs. This is the ranking categories by DB engines as of 2024, as of January this year, basically. As you can see, no matter what anybody might tell you, no matter how many booths you see of all these wonderful databases, relational clearly takes the cake. It's got 72%. It's not shocking. It's got about a 40-year head start on everybody else, which is fine. And it's just got a lot of data. SQL DBs work. They work really well, as I'm sure most of us here. Actually, here's a great question. How many here got to learn about databases when they went to some type of education, schooling or whatnot? Raise your hand. Now put your hand up still if it was a NoSQL database as well, not just relational. Yeah, not so many hands. So I'll be honest, I started on Postgres because it was free, open source. My school didn't have to pay for it. It was great. It worked for a lot of my projects at school. It worked. I didn't actually know, when I got hired at my company originally as a front-end engineer, I didn't know what we were doing at first. I had to really look it up and be like, what the heck is a time series database? I knew it was like a NoSQL. I understood that concept, but I was like, what is it for? Why is it needed? It was kind of awkward at first, but once I got the gist of it, I really started to understand. But it was definitely not something I learned in school. And this is the trends over the last 12 months. That beautiful pink line, that's vectors. You can clearly see the interest is strong. All the other ones, you know, they have some interest spikes. For the most part, though, they all kind of just hang out in the range of not very exciting. To be honest, databases aren't exactly the most flashiest thing in the world to begin with, except vector DBs. Those are different. So you'll have already heard me say a few names. You'll have heard me say a few companies. I'm not being particular about anything except maybe my own company, Influx. That one's just a preference. But with other ones, it's really just the ones that either I've worked with or I'm, familiar with DevRels at the companies. There are over 400 databases on the DB engines alone. And I can assure you DB engines does not include them all. There's no way it does. There's probably like 4,000 of them out there. These are just a few wonderful logos right here. Again, you're going to recognize some of these. You're not going to recognize. Maybe you'll recognize all of them, honestly, but this is just a few examples. So if I continue to use specific DB names, it's not me trying to be like, I'm advertising for that company or anything. It's just I'm picking the ones that most people are aware of. So let's compare and contrast. So these are the 5 things, for the most part, that databases tend to compare each other on, outside of the fact that they're SQL or NoSQL, or they're good at one use case versus another. And I'll get into it at some point probably, but it's also very fuzzy nowadays in the DB world. Databases, for lack of a better term, make their money off storing data. Who would have thought? And so that means that they have a vested interest in storing more of your data, not just like you personally, that's a different problem, but basically your company's data, they like to store it. So you'll hear a lot of companies be like, we can store everything. We can store it all. For example, Mongo now has a time series DB. Totally makes sense, I get it. It's a hot, way to make more money by storing more data. That doesn't mean they're bad at it, by the way. I'm just pointing out that although we are categorizing each DB as we go through this talk, many of them span and blur lines quite a bit, especially when it comes to AI and stuff like that. Almost every DB now has some type of AI category running along with it. So you've got your on-disk storage format, your primary index data structure, data compression, your hot and cold storage, and your durability and disaster recovery. Now these two over here are a little weird in that they used to be more relevant, but ever since things have kind of gone onto the cloud, to be honest, a lot of cloud providers offer these two things in various formats. So you can kind of take databases that didn't have amazing hot and cold storage or didn't have amazing durability and disaster recovery, and you can kind of build it yourself. It can just be built in. It's a lot more simple. So this is mainly the two different ways of columnar storage. So you've got your row-based, that is for the most part going to be your SQL DBs, and then you got your column-based. So you can probably already see this, but a row-based storage format, it's similar to how it's represented in the original data source. It's well suited for transactional workloads that require frequent updates and inserts. It also allows for a very efficient retrieval of those complete rows. Columnar storage is when each column is stored separately. This is better for analytical workloads that involves a lot of scanning and aggregating large data sets. So again, this is good for time series data. That's good for just your normal SQL data. And this is a much better slide at just, showing all these two different things. So you'll hear the words, I, especially in my world, hear a lot of OLAP. We compete with other OLAP DBs, things like ClickHouse, for example, things that are good for fast data aggregation, which normally means running like a downsampling task, saying, can you condense my average temperature instead of being every second? Can it be for the past, 5 hours? Can you give me the average? That would be an aggregate. High-speed compression, because you're normally dealing with a high ingest of data. These aren't so great for compression because normally you're not dealing with like an IoT sensor that's sending you data every second. You're dealing with somebody updating their name or an order or something a little more simple. So when it comes to primary index data structure, so basically the big thing to know here I actually don't really love this image now that I'm looking at it again, but basically the deal here is your primary index is how the database is looking for your data. So in a SQL DB, your primary index is normally your ID. So that normally means, or at least that's the index that can help you like join and stuff like that. Those are those IDs. So that makes it very simple for you to look for John because you know his ID, because you know all this other information about him. And occasionally you end up with secondary indexes. That can be something like John's email, for example. It's normally something more unique, though. Like, that's why it's normally IDs, is because they're unique. Yeah, basically like this. It uniquely identifies, it's like the page number of a book. The secondary key is more like an index page of a book. So in a time series database, this primary key becomes your timestamp instead of an ID. And secondary keys are normally picked by the customer. Those can be something like the value of like a machine name, for example, or a location. Then you've got data compression. So this is normally where databases tend to really occasionally stand out from each other when people do like comparisons of them, because everyone's compressor and decompressor is normally protected information, I guess you could say. It's the bread and butter of what makes them different and makes them profitable. It's what makes them, unique. But basically, different data types are better at compressing versus decompressing and so forth. Like for some DBs, you really want your data compressed super, super small for better storage for the long term. But normally the flip side of that is it's going to take forever to decompress them. Other DBs, like for example Redis, don't tend to compress very much because they're a hot storage option. And so they're really good at decompressing because they don't tend to compress that much, which is good for their overall use case, which I was just getting into right there, which is the hot and cold storage. Now, this can still be somewhat relevant. I know I said with cloud, you get different options. And really what I'm talking about there is the cold storage, the cheap and deep. That's like your data lakes, data warehouses, all that good stuff. But your high performance hot data, that's like, for example, tends to be where like Redis runs. That's running, in your cache. It's it costs more money to run it, basically. It costs more money to store that data hot than it does cold. Cheap and deep is for a reason. But sometimes you need your data right there, easily available. It's not something you can negotiate. And most people are somewhere in the warm. They're capacity optimized. Some DBs like ours come with a specific cold storage. Others, just kind of source it out to other database types, which is totally fine. But most DBs are going to be in the warm category. And durability and disaster recovery. This is critical. I don't want to say it's not critical or anything like that, but it is something where a lot of people nowadays can kind of solve this problem themselves. They just create their own secondary read-onlys. Some DBs come with it out of the box, which is great. It's definitely an important functionality that I would take a look at when you're trying to, determine a database for your fit, which we'll get into later. But just do keep in mind this is another thing where they tend to differentiate from themselves, is whether or not they offer this. All right, so let's go ahead and get into some DBs. So we're going to build our own company called Nordic Treasures. It's going to be like the Amazon of Nordic Treasures. We're going to sell some wonderful Nordic treasure products. These are all images I stole off the internet, but I do love them all, especially the Moomin cup, so cute. So we're going to build the foundation. It makes sense. We're going to use a SQL database. We're going to store our customer data, all the people who give us their name and email willingly. We're going to have their customer orders. Which things have they been buying? How much does it cost? And inventory. We're going to keep track of our stock levels, our cost, our descriptions, all that good stuff. And databases like this should be pre-designed. How many people have learned that mistake, I wonder? Pre-design your SQL DBs. They're not fun to redo, I can assure you. With joining tables, too. Keeping in mind, how you're going to interact with all this data, for example. Like this, your orders, your customers, your items, and your order items. This is a great format, and this is an entire subset of education, is basically designing DBs, SQL DBs for larger companies especially. This is like I said, this is going to be something that lives. You're going to retire and this will still be living in some cases, like it will live forever. So that's why it's an entire thing that people study, is actually how to properly design SQL DBs. Let it be known, I was not gifted with that learning, that education. My school was just like, good luck. I have the databases to prove it. They were very fat and very ugly. I didn't separate anything, I can assure you. New SQL, yes, that's right. Some things, they change. So one thing I did want to mention is new SQL DBs, and I specifically added this slide because it included some companies that I don't actually work with that much, whose names I barely remembered, and so I put this up here so I would recall this. But basically, they've taken some of the best parts of SQL and some of the best parts of NoSQL DBs and turned them into new SQL. And from what I can tell, most people actually quite enjoy using them. And big thing is people like them because they include SQL support. You're going to find that's actually a pretty big catch point for a lot of people when they're choosing databases. And I don't blame them, but they want to use SQL. It's the language they've learned, they get used to using. I'm not going to blame them for wanting to continue to use SQL, and that's one of the big benefits of these, is that they can kind of actually still take some of the use cases of NoSQL DB and give you the SQL language support, which is a big deal. That let me tell you right now. It's very important for sure for a lot of people. But yeah, so now you have new SQL. It's a new category. This is what I was talking about before when I said things tend to get very fuzzy and lines tend to be blurred. That's what I'm referring to. Now you deal with your document databases. So this is going to be your MongoDB. So this is where you're going to store stuff like your item data, which is going to be different depending on the item. Your sauna has very different descriptors than a jar of jam. For example, the jar of jam probably has ingredients. Your sauna probably has measurements. That would be an important thing to keep track of. The other thing is, these were the original DBs for customer recommendations. So nowadays, we tend to use a GraphDB for this. That's going to be the more common use case. But historically, this was the original, probably the original Amazon when it was suggesting books to you, if it did. I can't remember exactly. It would have suggested it using what it had in its document DB. Basically, your purchase history, your wish list, your browsing patterns. It was a little more rudimentary than our current GraphDBs are, but it worked, and it did a decent enough job. It wasn't as creepy as they are nowadays. They're much better at recommending stuff. They know you even better now. But at the time, it worked pretty well. It was pretty good at noticing patterns, basically. And this is really important for that item data because these are very manipulatable databases. So it's also very easy to be like, we're not selling this jam anymore, or jam in general, drop it. We don't need this information. We don't need this, this data store, this data columns, these rows. We don't need any of it, so go ahead and drop it, please. That's a lot easier in a document DB. So for example, this is how you store this kind of data in a relational. You've got a person named Mary. She's got a profession. She's a developer/engineer. She's got some apps, and she's got some cars. All very fun. In Mongo, this is how this would end up looking. So this makes it a little bit different when you want to search for things, basically, like when you want to try to find other people with the profession of developer, for example, or other people with the cars with the make of Bentley. Because the data is stored in like a JSON format like this, it's a lot easier to do that pattern matching. And it's also a lot easier to, for example, change the cars that she has. You can just drop that Bentley and you can go ahead and add a Cadillac or something, you know. It's very much easier to go ahead and change this up. Fast and efficient searching. So now we're into our search DBs. The biggest one would be Elastic. Who would have guessed? So they're great for keyword matching, fuzzy search, relevance scoring. You can get refined search results, so that's when things now become pricing. I only want to pay $50 for my sauna. I don't know what you're getting for $50, but that's what you want to pay. And you want it to be a 5-star rating, and for some attributes, you want it to only fit one person, etc. You want it to be brown. Those kind of searches, they're all powered by SearchDBs. And finally, they also allow you to do search analytics. So that's things like searching behavior and trends. What's trending right now, you know? In Nordic Treasures, what rye bread is the best rye bread? What's everyone looking for? Popular searches, etc. And obviously at scale, this is used by our web browsers, which are all powered by SearchDBs. And this is what it looks like when it's indexed. So this is an inverted index. So you got 2 different poems here, or rather sentences, not really good enough to be a poem. But basically, each one of these they've got the words, they put in a different document that says where these words are found, and that's the index. And that allows you to do that keyword searching that I was mentioning before. This is obviously how we get, like I said, at scale, this is used by almost every modern web browser. I shouldn't say every, it's definitely every web browser is using this. And for the most part, they send out their little, man, I can't remember the name for this. Spiders, searchers, I can't remember, but crawlers, that's right. They send out their crawlers to each website, and they're scanning not only the URL, they're scanning the actual content of the page, they're picking up words, and they're putting that in the index to determine when you search for things if this website meets it. Now, obviously an SEO engineer will tell you there's a lot more involved in that, and that's true. There's a lot of ways to make your website go to the top of Google search versus the bottom. But that is the gist of how these are actually going ahead and finding all this information to start indexing out. Enhanced performance. So now we're going to use something like Redis. We're going to use, and this is going to hold we're going to use an in-memory data storage that can be important for faster data access and improve system performance. It's stored within the RAM, so there is a higher risk of a data loss and a higher cost. So this is not where you store your overall user data that's going in your SQL DB, but this is where you store something like, I'm going to use an example that's beyond Nordic Treasures. For example, if you're Taylor Swift and you want to sell concert tickets, it's a very important thing that you would have your concert tickets in an in-memory data store. So that way then when you have 80,000 people trying to buy your tickets, you know how much stock you have. So you don't accidentally sell people more tickets than you actually have, because you cannot be making the query back to your database and waiting all that long because you have 80,000 people requesting these tickets. As we saw when that all went down, this is when this really comes into effect. Now, obviously, it can be used for a lot more mundane things, like current browsing history and preferences, items currently in a cart, real-time inventory, much more, down to earth, definitely still relevant use cases, but I like the Taylor Swift example because it's something that actually happened in the real life, and we can see when you don't use things properly, how painful it can be for everyone involved. I cannot imagine waiting hours to try to get a ticket, but some people are more dedicated than me. So this is how Redis is traditionally used. As I said before, it's looking in the cache. So it's saying, hey, how many Taylor Swift tickets do we got? And the cache is saying, not many. We've got about 5 left. Versus if it's saying, how many tickets do we have for a different concert? It's saying, I don't have that right now because I'm really busy with Taylor Swift. So why don't you go ahead and go look in our persistent data store for MySQL for this other less popular concert ticket that you're trying to go find, because I'm very focused on my task at hand, and I only have so much space in my memory cache to possibly hold everything. So I'm just focusing right now on the Taylor Swift tickets. I'll come back and deal with other stuff later, basically. And that's exactly how, for example, Ticketmaster was having lots of problems with the Taylor Swift stuff, but if you wanted to buy tickets to a different concert that was not Taylor Swift, it wasn't having so many issues. And this is it at scale. So you can also have, obviously, multiple Redis clusters. Yes, I'm using Redis as an example because they have lots of pretty, they did the work for me on this, and so I'm just stealing it from them. And so this makes it really easy if, obviously, you have some clients who are reading and writing, you've got clients who are just reading, you've got replication going on. And I've seen Redis DBs used in some really crazy ways. I think this is one of the DBs that's probably used the craziest. I love talking to people from Redis because they've got some amazing war stories, to say the least. So now let's get into the new DBs on the block. So those are, like I said, those are your most standard DBs. They're the ones you're most likely to learn about either through school or through a job. They're the ones you're going to be the most familiar with. This is where I come from. This is real-time insights, time series databases. So this is a little bit beyond Nordic Treasures sometimes, outside of the fact that time series databases are great for monitoring server infrastructure. So as Nordic Treasures is running and we have people on the website, we can make sure that our clusters are running as we expect. We can optimize. We can use something, like I said before, like Datadog. That's going to be an example of time series data going into a platform that allows you to monitor. But basically, it's good for high ingest data, things like IoT devices, the ability to compress that large data set that you're going to get from things like IoT without breaking the bank, the need to store multiple wide rows, timestamp with multiple values. And instead of indexes or values, you're querying based off of time. Like I said, the primary index in a time series database is always going to be the timestamp to make it faster for you to do a query like, in the past 5 minutes, what was the average temperature on machine 12, for example. It can obviously be used to identify in-demand and trending items plus seasonality. And I've already mentioned that before in another database too. Multiple DBs can do this. They can use for tracking revenue trends to enable pricing strategies and to track and monitor website performance. Another thing that I like to talk about is that these use cases are, again, beyond the scope of our Nordic Treasures company, but they're still relevant, which is things like physical monitoring. So you've got like warehouse IoT devices. That's actually where our company tends to do the best. That's actually where a lot of our customers are. Robotics data as well, shipment tracking, and inventory level tracking. And this is something that I wanted to point out, which is a different way of how this data is stored, because it's a little different than, like I said, how we think about a SQL DB. So for example, the timestamp is the main requirement. The only other thing you're technically required to have is a measurement, like server, and one field, which, as you can see here, a field is normally an integer set, something like CPU or memory. And then you can also have tag sets, which can give you more information, like a location. For this one, it's doing a host name and a location, though it's calling it US West, not just location. It's very specific. And yeah, that's basically how these are formatted to be stored. The next one is graph databases. So graph databases, like I said before, they power our social media for sure. They also power social logins, social connections, personalized social feeds, personalized product recommendations. The other big one, like I said before, that Mongo tended to do a lot, document DBs tended to do a lot at the beginning because they were available and it worked. Nowadays, it's almost always graph DBs. That's why it's getting better. That's why your recommendation list is getting better and seems a little more creepy and knows you a bit better. So they're great for relationship complexity. They're great for figuring out who's connected to who and how am I going to sell them this product because they're connected to who. Flexibility, it's a schema-free data modeling for enhanced adaptability. It's got rich relationships to uncover those patterns, identify influencers, and deliver personalized recommendations. And the other fun one, it's actually used by quite a lot of banks for noticing fraud and potentially odd out-of-place spending patterns. I've gotten to enjoy this once. When my bank sent me a text, I had the credit card on me. It's not like it was physically taken away from me, but they were like, these purchases are weird and not yours. And apparently that day I went to a restaurant, and in the US, they take your card away from the table. I know it's weird. But they took my card away from the table, and apparently the server had written my card information down, basically created a fake credit card, and went shopping with my card about 2 hours later. I was still in the same city, the same town. It's not like he bought stuff on Amazon. He actually went to like a physical mall. But apparently that was weird to my bank. That was so against my spending patterns of going to a physical mall, which I never go to, probably, going to men's shopping stores, which I'm not a man, and apparently I don't buy enough stuff for my husband because that was also flagged. And so I got a text like 2 hours after he made the purchase that was like, these don't look like you. We think it's not you. And I was like, that's really creepy and it's not me. So I guess, yay, thank you for that. But that was powered by a graph DB for sure. That was definitely something where they recognized my patterns. I have a profile at my bank. They know me from all the stuff that I do. That's why, for example, I no longer tell my bank when I'm traveling. And I travel a lot. I never get flagged. It's because where am I buying my flight tickets, my hotel rooms? On the credit card company, they know where I'm going. They know I'm here. They know the receipts. They have all this information. And they've created this pattern of, we know Zoe travels a lot, and we know the kind of countries she travels to, so we can easily tell when it's her versus somebody else. So again, this is how this would be stored in a SQL DB. You've got your customers, you've got sales, and you've got inventory. Great, all on its own. In a graph DB, looks a little bit more like this. You have person John, who buys a lot of Pepsi, and you have person Jack, who also buys Pepsi, and he's married to the person Valerie, and he also buys club soda. And if there was another arrow here, maybe it would say something like Valerie buys club soda and vodka, something like that. But basically, all of this can go back to John, and it can be like, we think you want club soda. We think other people, now imagine this at a bigger scale, obviously, like maybe there's many, many, many Jacks and many, many, many Johns to get this data more accurate, but basically, they think that John also wants club soda based off this connection. So they're gonna start targeting him with ads for club soda. If you've ever shopped on Amazon, I'm sure you've seen at the bottom of any item, hey, other people buy these other things with the item, and normally it's very obvious. It's like a toy, and the other thing people buy is batteries. You're like, okay, that makes sense. But sometimes it is a little more interesting if you've ever noticed some of them where it's like, it's a drink, but now it's offering you food, like nuts or something to go with your drink. And it's because other people who have bought these drinks also enjoy these nuts. And it's determined that maybe you'll also enjoy these nuts. At scale, this is also why, as some people say, it's creepy that things are spying on you. It can also just be that your friends are searching for things on the same IP address as you, and so it's starting to connect you. I get a lot of Google ads that are clearly meant for my husband, not for me, and it's because we're sharing, devices within a house within one IP address, and so I'm getting targeted stuff for him because it knows that we're married in some format. Obviously, not all of this data is shared. Not everything Facebook knows about me is shared with my credit card, but there's enough profiles of each one of us individually on the internet that companies, they can really start to figure out what we might like, and it's because of all the data they've aggregated from other people. Now the vector DBs. So you've got, like I said, visual search revolution, but also just revolution in general. Vector DBs allow us to integrate visual searching so you can look for specific items with images like Google search, but they also enable, more popularly, natural language processing by storing words, sentences, and document embeddings, enabling semantic search, similarity, and text generation, which is a ton of wording to say they enable ChatGPT. Also, as things progress, they will enable actual chats. Like, hopefully one day I'll be able to chat with a chatbot that's not completely useless and unhelpful. One day it will be a little more human-like. Maybe it will even pretend to be a human. I wouldn't be shocked if that's the next step. And this tends to be basically how they work in a gist. I'm going to be linking a QR code to a video from a DevRel at a vector DB company it's a little long, it's about 50 minutes, but it's very, very good at explaining the mathematics behind these DBs and how they work, which is way more than I have time for. It's more than I can explain in 5 minutes, that's for sure. But basically, they take these vector representations of the data they are ingesting, whether that be an image, a document, audio, text messages, whatever data they've got. They have vector representations for it. And with that, they're using, somebody once told me that vector DBs are just graph DBs on crack, because then they use nearest neighbor from the other vector representation, and they give you back results, basically. So they are using these dense vectors to find nearest neighbors and then resulting it back to you. I know, it's a little strange. Basically, it's a bunch of mathematical arithmetic on the underside, but basically it tends to match things to different things. Like it has like a mathematical equation to be like whether this is more male or female, whether this is like a verb tense, a country capital. It's making pattern matching and using math to do it. And like I said, this is more advanced than I can get into here. And this is a image basically of how this works. So you've got your query image and then images that it finds to be relatively similar. And this is also all based on the underlying model underneath all this as to whether or not it's good or bad to an extent, because each one of these embeddings is different in each model, basically. Each model is looking for slightly different things. And so as you can see, this one's pretty good.
I mean, I would say that that really dark plant up there on number 2 is a little strange, doesn't really match to me personally. I don't know where it's pulling that one from, but for the most part, this is pretty good. The mountain range especially is quite good on this one, but this is basically how it's starting to pattern match.
And this is the RAG model. So this framework, which always includes a vector database, a language learning model, and a prompt as a code, is known as augmented retrieval generation. Everyone just calls it RAG, and serves as the foundation for developing language learning model-powered applications. Again, I took this from the DevRel at Zillis because it was perfect for explaining how this works. But basically, user asks a question, the vector DB has all the external knowledge that it's been fed and is stored. It takes the prompt, it puts it into the language learning model, and returns back the answers. So that's what I was saying when it comes to vector embeddings, is it's all based on the language learning model. So for example, you could say that ChatGPT's language learning model is pretty good. It's been developed for many years, that's probably why it's pretty good. But you've got simpler language learning models that, for example, somebody like I would produce, and it would produce a bot that's not very helpful. To be honest, it just wouldn't answer things quite as well because that's not the field that I've studied in. But that's also why there's so many language learning models available on the internet and so many research papers written about them, is because basically, depending on how good that language learning model is, and depending on your vector database just stores the embeddings, so that's pretty much just all storage. But it's really the LLM that makes your bot good or bad, or how it responds good or bad, if that makes sense to everybody. But just keep in mind, VectorDB is for storing the vector embeddings. So for example, this in the future could be for Nordic Treasures. I'm looking for the ideal sauna for parties. And it found us some wonderful saunas that I found on the internet that I thought were really fun. And I quite enjoyed them. I really want the tram one personally. It's my preference. So we're going to go ahead and wrap up. So this is something you can take a photo of. So that is DB Engines. That's where you will find a ton of information. It's a website that really needs updating. Just be clear here. It looks like it's from the early 2000s. But it's great for getting all your DB information. It's good for seeing rankings. This is the InfluxDB website if you want to learn more about time series databases. We also have more information about databases in general. Then you've got your vector DBs one-on-one. That's the one that I mentioned that was the YouTube video. If you want to learn about how these work on the underside and the math behind them, that's the best video to watch. So I commonly get asked, Zoe, how should I compare databases for my own use case? I'm going to tell you what our salespeople tell our customers. Your data is unique. Yes, that's right. You have a unique data set, a unique problem. Sometimes your problem isn't too unique. It's been done before, you could say. But funny enough, even in factories where you would think the next factory should be just as similar as factory A, they make the same product, they're from the same company, somehow they end up with unique data sets because their engineers want different data. Or, it's one of those things where although you can take these comparisons, you can go online and do SQL versus whatever, InfluxDB versus other time series database. I would still suggest when it comes down to it, it's everyone's job to kind of test with their unique data set and make sure that you're happy with the things like the compression, the decompression, how fast your queries have to be, how slow are you willing to wait 5 minutes for it? Or does it need to be lightning fast, those kind of things? Or how often are you going to be editing this and dropping this? All of these are good questions to ask, but do just keep in mind that although I've been explaining all the different types of databases you can use and some of their more common use cases, I still suggest doing the due diligence of testing things out. It's obviously the one benefit of going with something that's very popular is that there will be lots of information about it. I'm going to be honest. The more popular the DB, the more info you're going to have. But sometimes it is worthwhile to go for a lesser known DB that actually is really powerful and good for your use case. And just some final resources. I already kind of added these before, but this is the Influx Data website. This is our community where we do a lot of small projects. For example, that one right there, Plant Buddy, helps people monitor their plants at home. I'm using it at scale in my greenhouse, but this one's just for an individual plant with a bunch of fun little IoT sensors. Could be good for like a high school project. We also are an open source database. I never mentioned that until now, but we have an open source version. So when I say you can run your own home project, I'm actually being serious. And then these are just the getting started. We have a Slack community. If you ever want to reach out to me, feel free to find me either on Slack or LinkedIn. Those are the two best places. We've got a GitHub, docs, blogs, and our own university, which helped me build out this slide deck once upon a time. I've taken it all on my own at this point, but originally they helped. Thank you guys so much for coming. We're pretty much at time, but if you have any questions, feel free to just come up. And otherwise, everyone go enjoy lunch, and I hope you have a fantastic conference.